Look at a straw resting in a glass of water. At the waterline, the physical object appears severed, completely disconnected from the top half. This happens because of refraction. Refraction occurs when a light ray crosses the boundary between two different transparent materials and changes direction. Light travels perfectly straight through the air, but watch what happens when a laser hits a water tank. At the boundary, the beam snaps downward. We can calculate and predict exactly where the light is going to go. The severed straw in the glass results from strict, measurable geometric rules. To calculate the spend, we draw a baseline, a dotted line perpendicular to the surface, called the normal. Snell's law provides the math. It states the ratio of the sine of the incidence angle to the sine of the refraction angle is constant. That constant is the refractive index, a fixed mathematical bridge between the incoming and outgoing angles. If the second material's refractive index is greater than 1, it's optically denser. Here, light is forced to bend inward, pulling closer to the normal. The boundary between two materials acts as a strict mathematical filter that dictates exactly where light is allowed to travel. We can see this law in action by passing light through a parallel-sided rectangular glass slab. Light bends inward entering the denser glass, then bends outward exiting back into the rarer air. Because these refractions occur at parallel surfaces, the final emergent ray remains perfectly parallel to the original incoming ray. Looking through a flat pane of glass doesn't change the angle of the world. It simply shifts the image laterally by a calculable distance. This optical shift becomes even more pronounced when we try to look at objects submerged inside a tank of water. Light rays from point O at the bottom bend away from the normal as they exit the water. Our brains project those exiting rays backward in a straight line to a false image point, creating the apparent depth. Our brains prioritize straight lines over the physical location of the object, following the geometric logic of Snell's law. To understand why light bends, we have to separate the concept of density into two distinct properties. Mass density refers to how heavy a volume of liquid is. Optical density is the ratio of the speed of light between two media. The relationship between turpentine and water illustrates how these two properties can diverge. Turpentine has a lower mass density than water, meaning it is physically lighter and will remain floating on top. Yet turpentine is more optically dense than water. It bends light more severely than the physically heavier liquid beneath it. Optical density reflects how much a material reduces the speed of light. Because turpentine slows light down more than water does, it forces a more aggressive change in direction. The invisible, mathematical breaking of light across different materials governs our visual reality.